Welcome everyone. In this video I'm going to show you another iteration of my milling table. So originally I bought a milling table with a fully mechanic mechanism, and then I decided to upgrade it by putting stepper motors on both X and Y axis. And then now I further developed this thing, so now I can measure the displacement of both axes via two magnetic encoders. And in this video I'm going to show you all these details that I did, and then I'm also going to teach you how to do it yourself. So you can see all the parts which were used during these, let's say, iterations, and I will tell you how I built up everything step by step. So the milling table is here, and this is it. And as you can see, we have two stepper motors, one on the X-axis and another on the Y-axis. And I already published 2 videos about this thing. First, I disassembled the original product and I tried to explain what is what inside this mechanism and how we can improve it. And then in a following video, I added 2 stepper motors to the axis, and the main thing was to add the bearings, which are thrust bearings, so they can withstand the axial forces. And then also I printed these couplers or brackets to be able to put the stepper motors on the mechanism here. And then I also, of course, added the stepper motors. And then I was just using a simple circuit with a joystick, with a similar joystick as you can see here. And then I could move everything back and forth. But of course I did not have any clear information about the position of this table. So now we are in the most recent iteration of this project, which is possibly the final iteration, where I improved several things. So first of all, in the previous project for this milling table, I was using this kind of pancake stepper motor, which is nice because it's small, it's quite compact, but I thought and still think that this doesn't have enough torque. But it was good enough to move this milling table around, but I could hear that the motor was struggling even at the highest current. So then one of the iterations, new iterations, was to replace this motor. And as you can see, we have much more bulky motors there because this is the new guy that I'm using. So it's like 2.5 times larger or something like that, with much higher torque, of course, but much more hunger. So you need more power to run them. But of course now I can move everything quite smoothly. So this was one part of the iteration. And another part, which is very important for me, is I added a magnetic encoder. So I have a video where I showed you this magnetic encoder. This is the AS5600. And what I did here, I made a mount for the stepper motors, and then I put a diametrically magnetized magnet here, this tiny guy. I put it on the shaft, and then in the bracket, which looks something like this, I put in the magnetic encoder, and then I screwed it on the back. But this is not the final version of this plastic bracket, and as you can see, I have several of this plastic thing. Actually, this is the way of the evolution of these things. So I just wanted to quickly print something. You can see these 4 nuts here. I wanted to quickly print something just to put it on the back of the motor like this. I even had a space here for the cables, just to test if I can read the encoder properly. And then I wanted to have a bit more compacting, but I saw that, okay, this will be a very weak construction and this looks quite stupid. So then I moved to this one, but there is still a gap between this part of this object and the top part. So then at the end I just merged everything together. So I have a proper distance between the top of the chip and the magnet and everything. And that is the final plastic part which is mounted on the back side of these motors. Obviously I cannot really show it because now everything is assembled, but please believe me. So it's in plastic cradle, let's say, and that is just sitting on the other side of the motor, like this. And then as the motor spins, the magnet which is attached there, this kind of magnet, rotates, and then as the magnetic field is changing with the rotation, that will be captured with the Hall sensors inside this chip, and then it's converted into some numerical values. So the other big thing is the encoder. And why the encoder is important is because we don't have any other information about the displacement than just some kind of scale here and some kind of scale on these handles, but that's not really the best thing. So what we do is that we are reading the turns, or more precisely, we are just reading the displacement of these shafts, both the X and the Y shafts. And then based on the displacement and based on the pitch of the both screws, they technically just have some threaded rods on both axes. So based on their displacement, we can calculate the linear displacement of the two axes. And in this case, it's very simple because this thing has very simple threaded rods which have 1 millimeter pitch, which means that if you do one turn, so you just rotate it 360 degrees, that will result in 1 millimeter linear displacement. And then what we do is that we read these turns with the magnetic encoder. Actually, we divide the turns into degrees, since this magnetic thing has roughly 0.09 degrees resolution, but of course we don't need that high precision because this mechanical stuff is not rigid enough. But we can basically read each steps at very high microstepping, which is quite nice. So we read the angular displacement of the shaft, and from that we can calculate the linear displacement of both axes. And then here comes the circuit. So this is actually a quite simple circuit, and now I made it on a PCB or some kind of perf board, so everything can be seen very nicely. So what we have in the center, we have an STM32 blue pill, so this will be the brain, and then it communicates with two different circuits. So one circuit is the DRV8825 stepper motor driver. It's just enough for these kind of stepper motors. And then I put a lot of jumper pins here. So on this side, we have jumper pins for the motor. So we just have the jumper pins of the stepper motor, as you can see, and just plug it in here like that. So that's very simple. And then on the other side, you can see these 2x3 pins with the jumper header here and there. And those are the pins for the microstepping. And now we are at half step stepping, which means that one turn for the stepper motors will take 400 steps. But then we can replace these or add more jumper headers. So based on how much thing we leave floating or leave connected to the 3 volts, because the other side is all 3 volts, so the logical high value. Based on that configuration, we have the different microstepping, and we can go down to 1/32 of a step. So that will result in 6,400 steps per turn, and that's a very, very fine resolution. And then there is another set of pins here, jumper pins. So those are for this big spaghetti here. So we have this Nokia LCD, and that needs SPI. So we will use the SPI pins on this thing. And of course we have the joystick, which of course needs some analog pins because we read the output voltage of these potentiometers inside the joystick. So all those pins will be treated here. And then we have another pin over there, which is the B12. and that will read the switch, because this is also a switch, as you can hear. And finally, we are also using the I2C, which is B6, B7 pins, and they go to this TCA 9548A I2C multiplexer. And what this chip does is that it multiplexes the I2C signal. So that means that we can communicate with multiple circuits with the same I2C address. Because one of the drawbacks of this AS5600 circuit is that you cannot change the address of it. So all of them have the same address, which means that if you want to put multiple chips on one single I2C output, for example here B6, B7 on the microcontroller, then there will be a conflict on the bus and it will not work. So what you can do, you use this multiplexer, and then you switch the channels, which starts at 0 and finishes at 7. So you have 8 channels, and you can switch between these 8 channels, which means that you can connect 8 I2C devices with the same address to your microcontroller. But of course now I'm just using 2 channels here, and those are going out to this connection here. And then I can connect the wires for the encoder. So then that's also solved. And then, as you can see, this is a 3D printed front panel. It's a bit wonky and it's a bit not too perfect, but it does the purpose. But what this allows me is that I can make a very ugly cut, because it's quite pain in the butt to cut this plastic. So I can have an ugly cut, and I just have a bit larger area covered with this 3D printed front panel, and then it looks more or less aesthetic. So then we have another set of pins here, which is just the plus 3 volt and the ground, so I can connect other devices to it, but mainly I will just power the LCD and of course the joystick. And we have the power input for the stepper motors, so this is just a 2.1mm jack. Of course we have the 100 microfarad capacitors, and that's all. We also have heat sinks on these 2 chips for the stepper motor drivers. They can get quite hot. I actually burned one of my finger with it, but it doesn't matter. And yeah, technically this is all. So what I will do now, I will reconnect everything, and I will put the box together, assemble everything, and I show you how these things work. So how the stepper motor driver drives the axis, and how the encoder shows the displacement of this thing. So let me put everything together, let me assemble this box, and then I will show you all the things. So I'm back with the assembled box. So this is now in one piece, and hopefully everything is working properly. One sort of mistake I did is that I have 2 short wires for the encoders, so the box will be in this funny position, but hopefully you will see everything on the display. So once again, we have this milling table with 2 stepper motors, and on the back side of the stepper motors we have 1 each magnetic encoders. And then these magnetic encoders provide some information for the microcontroller, and based on this information we can display the amount of displacement in millimeters, both on X axis and Y axis. So now I just connect everything, and we will see what happens. So we have a USB cable and our mobile charger, and you can see that the display is on, the message is there. And I made several different items in a menu. So first of all, I want to show you and demonstrate the joystick. So we have this joystick, and both X-axis and Y-axis have a independent potentiometer. And the output of the potentiometer shows the position of the joystick. And in the 0 position, when it is in the middle and untouched, it is roughly at half of the maximum output voltage. And what we see here is basically the half of the maximum amount of levels that the AD converter can distinguish in this microcontroller. Since I'm using the STM32, this means that this microcontroller has a 12-bit AD converter, and the 12-bit AD converter is capable of distinguishing 4096 different levels, so from 0 to 4095, and then half of it is 2048, so this is floating around that value for both axes. And then so this is the top of the device, but of course the direction of the text pretty much tells it. And then the joystick is replicating that coordinate system, and also for this. So when I move the joystick up, the Y value should change, as well as when I move it down. And when I move it left or right, then that should change the X value. And the same happens here, that when I move the joystick up, then the table goes up. When I move down, the table goes down, and the same for left and right. And here I just want to show you the values for the joystick. So if I go towards the right direction totally, then the Y goes to 0. And when I move to the left, then it goes to 4087, which is almost the highest value. And this has to be tested before you put everything together. As you can see, then when I move to the right, which is usually considered as a positive direction, the value actually went to 0. So you have to handle this inside the code. And of course, when I explain the code, you will see how this works. And now I move the joystick up, and then X goes to 0 or nearly 0. And when I move it down, then it goes to the maximum value. So this is what happens. So then if I press the button, then I move in the menu. So now we see the millimeters. And now everything is 0, because whenever you start this thing, it's teared out. So wherever you start, regardless of the position of the milling table, you will have 0 values. And we don't need the motors to change the value here. So what I can do, I can start to turn this or this handle. I remove these things because they are rattling and they are annoying. So when I start to move this, you can see that the Y actually changes. And it changes in the negative direction because this comes towards me. I can have something, an object, something that can help us to see the movement of this table. So we have this duck, and then now I just keep this moving, and the duck should come towards the bottom of the display, so it comes, it goes this direction, and then you can see it here that the value goes to minus. Just to have some comparable values, I put this back to 0, and then we do some experiments, or I just set it to 5. It's just easier to add or subtract from a nice integer. So this is now at 5 millimeters. This is our initial position. We have a caliper here, and what I do, I just measure the distance here, which is totally independent from the Y value. But I just want to see what is happening here. So now this shows 2.66 roughly. So I move back to 0 on this, and then this should show 31.65 something. So let's see what happens. So I don't move this, and I go back to 0. So I just want to see if the displacement on this table is roughly the same as the displacement on the shaft of the motor, and ultimately on the threaded rod inside this milling table. So I go back to roughly 0. So this is more or less 0. And of course now this gap increased, and that should be a 5mm change. And it's almost, so now we are at 32.8, I would say. So it's a bit more than 5mm, but that is due to the different flows of this mechanical thing. But it works more or less, and of course it works with the X as well. So now I'm going in the negative direction, which is towards the left, and then you can see that the duck is slowly going towards this hand here. And then of course this goes minus. So now I move to the next menu, just for fun. So here I just print the total degrees of the turns of the shaft. So now I increase this, and of course every 360 degrees is one total turn or 1mm displacement. And this is just some interesting information for me. And then here we can set up a new zero position. And what this means is that whenever you move this to somewhere and you want to have that as a zero position, then you just push the joystick and then it prints you that the reset is done. So now I move to the next menu, and then these should be 0. So 0 here and 0 here. And you can do this whenever you want. And I will show you in the code how it works. So now let's put some power in this socket here, and then we will use that power to move it via the stepper motors and see what happens. And this will be probably noisy, so while I'm preparing this thing, I just want to tell you that you should decrease the volume on your device, because these motors and the mechanical stuff are quite noisy. So now I connected everything, and then I just move to the millimeters, and I just move with the joystick. So you could see that this moves, and of course I set the speed to slow because I want to move just tiny bits, and I move with this. But you might have discovered one mistake when you see this. So this should be the X direction, and this direction should be the Y direction. But it's the opposite because I messed up the wiring. So I put the X output to the Y input on the microcontroller, and I put the Y output on the X input on the microcontroller. So I just have to swap some cables, but that doesn't do anything with this demonstration. I just missed the 2 wires. So as you can see, it moves in the Y direction, and then we get quite nice precision with the millimeters. So now these numbers are expressed in millimeters. So as you can see, if I just slightly touch the joystick in a certain direction, then the number just changes a little bit. So this is like 50 microns, something like that, or 30 microns. And of course you can control this with the speed. But you can see that at least based on the displacement of the shaft of the motors, we can move quite tiny movements. And you can see that this duck is also moving like very gently. So in fact, we can try something. So I put this ruler here, and when I'm editing the video, we can see some kind of reference points, because I don't really see it right now. And then we can see how the numbers here are reflected in this. But please notice that the camera distorts the image quite a lot. So it might be that the distance is not really the distance that we see, because we are not looking at the scale like totally perpendicularly, and also the field of view is distorted. So this is just a small action camera, so it cannot flatten the image very nicely. So now I just move, let's say, 1 centimeter and see what happens there. So this was more than 1 centimeter, so it will be enough for our demonstration. So as you can see, this works quite well, and then of course we lose some precision because of this mechanical stuff. But once I have a bit more money, I might buy the big brother of this, because then that is assembled with lead screws and proper bearings, and therefore I can build that thing in a better way than this. But the main principles here is that we can control this milling table with stepper motors. So basically we can turn this into some sort of numerically controlled milling table. Then we can control the stepper motors with the joystick, and then we can read the position of the milling table based on 2 encoders, and there we apply a trick with a I2C multiplexer, because these encoders have the same address. Therefore we need this multiplexer to be able to read it or read them simultaneously. And then of course we print all the information on the display. And in fact what comes now is that I will show you the code and go through it step by step, but I can already tell you that if you need this information on your computer, that will be already in the code. You just have to remove a few comments, because I coded this in a way that if you modify the code just a little bit, you can send all these numbers to your computer. So you don't really need this box with the display, with the joystick, and then you can send the output of the encoders straight to your computer. So I think this is basically the final version of this product, except I will replace these short cables. I have already ordered some better cables. This is just for testing. And now we will go to my computer and we will go through the Arduino code, which is on the microcontroller in this box, and we will see how this works in the programming point of view. So let's go to my computer. So let's go through the source code, and as I already showed some of the parts that I'm going to show here in this video, I will skip a few things, but I will always give you a reference where you can find those skipped things. So we need the wire library because we are using the AS5600 magnetic encoders and they use I2C. We need the SPI because of the Nokia display, and we need the Excel stepper library because of the stepper motors. And then we have two stepper motors. So this is how they are defined. So these are the pins for the direction and the step for each stepper motor, and then I just simply call them stepper and stepper 2. And then I have three pins which I use as inputs. The analog X and the analog Y pin, they come from the joystick, and of course I have a button in the joystick, and that is also read by the PB12, so you can see which pins I'm using. And I messed this up. If I don't want to disassemble the box, then I just have to flip these two pins and everything will be alright. And then I have variables, so these two are saving the values of the AD converter, so I can use them throughout the code. These were used just for testing purposes, so it doesn't matter, but I was just testing what happens when I push the joystick in different directions, so how the numbers change, and then I wanted to see if I can increase or decrease the value of a variable with the joystick. So this is why I kept this in the code, but you don't need it, so I commented it out, as you can see. We need two numbers to store the values of the distance. So this is the distance which is shown in millimeter, but I think the name of the variable pretty much tells what it is. And then I have two sort of timers. One is the button timer, which will be used as some sort of debouncing, and then I have the update timer, which is the timer for updating the display. And then I have this button MINIQ counter, which is a value which is changed with a interrupt service routine. So what I do here is that I press the button, that is connected to an interrupt pin, and then that interrupt pin will be handled in the code, and it will increase the value of a variable, and that value is basically the page which we are in the menu. So since we are using the interrupt, we have to use it as a volatile, which is just used when we can change the value of the variable outside the main code. So we have to use the volatile. And then this is just to keep track of the change of the button menu counter. So I will show you how this works, and you will understand why I have like two variables to store the status of the button. And then this big chunk of the code is taken from another person. You can find the original code here, but this is a very nice implementation for the Nokia display, so I use this. You can also check this person's channel, because he has a lot of valuable demonstrations. So basically this is just copy-paste, but one thing that you have to notice that the Nokia 5110 display uses the SPI pins. So those are pretty much standard, and there are some other pins on the display, and they have to be declared, but they are treated in this library. But here I just listed all the pins, so you can connect them according to these and these numbers. And then this is one thing that I already showed in another video, so I will tell them, but I will not really go into the very details. You can check the other video if you are really interested in this. But we are just using a few variables here. One variable will read the status of the magnet, and then we read the angle from the encoder in two portions. So the low byte and the high byte stores that, and this -1 means that this belongs to the encoder 1. So whenever you see a -2, like here or here, that belongs to the encoder 2. So we have the raw angle, which is just the raw angle coming out from the encoder. That can be anything, because when you start up the encoder, the magnet is somehow oriented related to the position of the encoder, so it can be anything. And then we can convert this number into a normal degrees angle number, because the raw angle was just some kind of digital number, and then this is like the angle represented in degrees. And then we have these quadrant numbers. I use this to split up the 360 degrees into 4 equal portions. So every 90 degrees is a quadrant. And what I do here is that I can take care of the direction of the rotation. I will show you how this works. And then we keep track of the number of turns. We have the corrected angle, and then we have the start angle, which is just the starting angle when you powered on the microcontroller and the other devices. And then the total angle is just the total, like, accumulated amount of turns expressed in angle. And then this can be used for example, to update the display, because you can, for example, read the total angle and read the previous total angle as well. So whenever the angle changes, these are updated. And then whenever this changes first, and then if it is not equal to this, you can enter a function and then update everything. And then this is the encoder timer, which is just simply the time interval for reading the encoders. And this is the same as I just told you, but for the other encoder, so I'm not talking about this, but I talk about this encoder counter. So this is used to keep track of the active encoder when we are reading it with the multiplexer. So this value changes between 0 and 1. So we have the encoder 1, then that belongs to the number 0 whenever we are looking at the value of this variable. And when this value is 1, then we are reading the encoder number 2. So we are here in the setup. We have to start the wire, the I2C, and then I also start the serial because, as I said, we can print everything on the serial port if we want. That is already implemented, so we just have to enable it or not. Then we start the display. These are pretty much standard things, and with this print LCD function, I just print some welcome message. Then we have to take care of the pins. So we have one pin that we have to sort of declare. We don't have to declare the analog pins, which are reading the pins on the joystick, because that is taken care of the analog read function. And we do not have to do anything with the stepper motor pins, because they are taken care of in the Excel stepper library. So the only thing that we have to take care of is just the joystick's button pin. So that is done here. We use the internal pull-up resistor, and we also use this pin as an interrupt pin. So that is done here. And whenever there is a change on the pin, then we trigger the button pressed function. Then here, this is same for both the stepper motors. So we just set up some kind of maximum speed, acceleration, and speed. And the reason why this is 0 is because we are using the run speed in the loop. And if this would not be 0, then whenever the code reaches the main loop, it would automatically start to move. So this has to be 0 in the beginning. And then we have to read the starting angles of both encoders in order to tear the values of the encoders. So we switch to the first encoder, we see if the magnet is there, otherwise the code will get stuck here. Then we read the angle, and then we note down the start angle. So every time we have any kind of motion after we started the device and these codes are completed, then the start angle will be subtracted from that value, whatever we read after that. So that makes sure that we start from 0, basically. So the same exercise is done for the second encoder, and we are done. And then I clear the display. And then this is what happens in the main loop. So we check if the button was changed. If it was changed, so we pressed the button, then the menu will be updated. And then we read the two AD pins. So we read the X and the Y axis. Then, if we have to do it, we step both stepper motors. So you can see that they are using the run speed function. And after they stepped, we update the LCD. So basically, if there was a motion, for example, you will see different numbers on the display, for example, in millimeters or degrees. And then here, when 125 milliseconds elapsed, we also go through the two encoders and read their values. So we switch to the first encoder and read everything. So we know what was the angle and what was the direction. So we know the final position of the magnet as compared to the encoder and so on. And then we switch to the other encoder and do the same exercise for the other encoder. And then we just refresh this value. So this timer basically restarted and it starts counting from 0, and then it will avoid this part as long as 125 milliseconds haven't elapsed. And then this goes over and over. So let's see what is in this check joy button function. part is that if we press the button, then of course this is changed, but this was based on the previous value, which we always change here at the end of this function. So we always change it when we are able to enter this part. So if this is changed, then we clear the display, and then we set the font size to a small one, and then we see what is the value of this. So we enter in a switch case statement, and we see what is the counter. If it's 0, then we basically print the steps. So we are in the menu steps, and we want to see it on the X and Y. And these are sort of stationary parts, so we never update this when the loop is running and we are not changing the menu, but we are just reading the encoders. If this button menu counter was 1, then we replace the top text to millimeters, and then we put X and Y in the corresponding lines. And then if it was number 2, then we print degrees and X and Y. And then if it is 3, then we just print a text for the user to do something, so something will happen. And in this case, this is the menu where we can reset the original position. So this will be used to put the origin wherever you want in the milling table. And then we have this read analog function. So this is the read analog function. So there are 2 branches. So there is an if else statement in this part. And let's see what happens when the button menu counter is not 3. So when it is not 3, it is either 0, 1, or 2. So when it is one of these numbers, we have to read the 2 pins for the joystick. And then based on the value, we do something. And I listed my values, what happens when I move the joystick to one of the extremes. And here you can see the numbers. And based on this, I could set up the logic behind the behavior. So what happens here is, when it is larger than 3000, we move to the negative direction with 200 steps per second. And this is why my milling table was quite slow. I set the microstepping to 400 steps per turn. That means that if I just do 200 steps per second, it will take 2 seconds to move only 1 millimeter. So this can be changed, but for me, for the demonstration, it was perfectly enough. But 400 or even 800 can be doable. It depends on your requirements. So then, so if we pushed it towards one of the extremes, then we move in one direction. And if we pushed it towards the other extreme, still on the X axis, then we move in the opposite direction with the same speed. And if we are somewhere in the center of the joystick, so somewhere between 1001 and 2999, then the speed set to 0, so the stepper motor will not move at all. I forgot this. Now it's good. And then we do this exact same for the y-axis. So if it's larger than 3000, we move in a direction. And then if it's lower or smaller than 1000, then we move in the other direction with the same speed. Otherwise, if none of these conditions are fulfilled, so we are roughly in the center, then the speed is 0. So this was the if part. So we have the else part, and this is quite simple. So what I do here is that if we are in the menu number 3, which is the reset menu, then all we have to do is we push the Y joystick up, and that is done with this kind of condition. Then we reset everything. So we reset the position in the stepper, in the access stepper library, and then we reset the position in our variables. And then we let the user know that, hey, we updated everything to 0. So this part takes care of this resetting. So whenever you move somewhere with the XY axis, and you want that to be your starting position, then you move to the menu number 3, the reset menu, move the joystick up, and that will reset everything. And from that will be your 0 position. So of course these are not really visible because they are implemented in the Excel stepper library, so we don't look at these functions, but we look at the update LCD. So this is the update LCD. So what happens is that if 250 milliseconds elapsed, we enter this part. So we just update this function 4 times a second. If you think that this is too small or too large number, you can change it, of course. So we set the font size to small, and then again we are using a switch case statement to check where we are standing in the menu, and based on our position we do something. So we print a new text to the top, but this might not be necessary because we can only update the changed things, and these are more or less stationary, but let's do it like this. So first of all, we put the cursor in the second line to the 20th pixel. So this is second line and 20th pixel here. And we just erase that line by printing a lot of spaces there. And then we print the value of the potentiometer. So it's a decimal number, and this is how we should do it. So 8 characters are like spared for that string. It's in a number format, and it will be put in the buffer. So we put that in the buffer, and then that buffer is printed to this location with this function. And then we move to the 4th line. We erase it again from the same position, so from the 20th position. And then we do the same with the y-axis value. And then we finally print it. And then if we want to have the values in millimeters, which is the menu number 1, we calculate them first. So what we do here is that we have the total angle, which is the total accumulated amount of turns expressed in angle. We divide it by 360 because we know that the pitch of the threaded rod is 1 millimeter, so we can do this very easily. So we divide the angle with 360 degrees. That gives us the distance traveled in millimeters, and for my configuration I have to multiply it by -1, so I get the proper directions and the proper numbers. And then I do the same for the other axis as well, so that's the y-axis. And what we do here is a bit different. Until here it's fine. We have the, let's say, headline, and then we have a position, which is the second line and 12th pixel. We erase that line, and now we use this D2STRF. And what happens here is that we want to print this value, with this variable. We want to use this long string, so 8 characters, and then we want to have this much decimals. So this can be printed, for example, as 1.345. And then we want to put it in this buffer. So this is the sort of array where the output is stored. And why I do this instead of this? Because this number here is a float, and this SNPrintF is not capable of handling floats. So here, this D2STRF can work with float, so floating point numbers, and then we can finally print the floating point numbers. So first we just take care of it, and then we of course print it on the display. And then we move to the line number 4, and we do the same exercise but for the y-axis. And finally, this is very simple, so we just print everything in degrees. So what we do, headline is printed, then the space for the output number is erased, and then again we have a floating point number, so we use this D2STRF function, and then we have the total angle which we want to print we want to print it in an 8-character long string, and then 2 decimal points is enough. So let's say 345.32, and then that number is put in this array, and then it's printed on the display to these coordinates. And then same exercise but for the y-axis. So this is the total angle coming from the other encoder. And then when we are in the reset menu, we do not do anything. And after everything of this, or after any of these things happen, we update the timer. So then here the counting starts again from 0. So we are done with these things, and now comes these things. And actually, this is already explained in another video, which you can see up in the right corner. So I will not really explain it what happens in very details, but I will just quickly go through it. So let's see what happens in the switch encoder part. And this is what we do with the multiplexer. So this is the switch encoder function. So what we do here is we select one of the encoders, and we step into one of the conditions here. So what happens in the first, so when the encoder 0, in our case the encoder for the x-axis is selected, we first start to communicate with the multiplexer, and then we tell the multiplexer to select the first channel, which is the SD0 SC1, and that's done. And after that we just switch to the encoder number 2, which is here is the encoder counter equals 1. So then we switch to the y-axis encoder, but the code steps out from here, so this will be not performed in this iteration. So first, this is done, we selected the encoder, so let's see what happens with the selected encoder. So first of all, we read the raw angle from the encoder, and then we correct that angle according to our coordinate system and so on, and then we check what was the direction, whether we have to subtract our displacement or add our displacement, and so on and so on. And here I have to notice that this thing is also explained in another video, which you can see in the upper right corner, so please also check that video if you need more details. Here I will just explain it in a very quick, rushed pace. So now we are here, and we switched to our first encoder with the multiplexer. So first, now we go to the encoder's address, and then we want to read the 7 to 0 bits. So we read it, and then we technically just read that number. And then we again tell the same encoder that we need the other part of the number, the top bits, the missing 4 bits. So we read it again. So that is done in these 2 parts. And now we have the lower part and the top part of the whole number. So we have to combine it in some way. And what happens is basically here. And as I mentioned, this is already explained in very details in the other video. So what we have here is that we have 2 8-bit numbers, but we want to build only a 12-bit number from this. So first, with the high byte, we shift it 8 bits towards the left to put it in a correct way. And then we combine this shifted high byte with the low byte using the bitwise OR operation, and that will be our raw angle. So the raw angle is just some kind of digital number. But then we know the resolution of this device and everything, so we use this kind of formula to express the angles in degrees. And finally, if you want, you can remove the commented lines, or remove the comments from these commented lines like this, and you can send everything to your computer. So now we have the degrees angle, but we have to convert it into some more useful data, so we have to correct it to our own taste, let's say. So that is what happens in the next step, which is the correct angle. And once again, this happens for the first encoder. So what happens here is that we have the corrected angle, which is the degree angle which we just recently measured, minus the starting angle. Because if you remember, in the very beginning, when we started the whole circuit, in the setup part of this code, we read the angle of the encoder. Because how the encoder works is that based on the position of the magnet, which can be an arbitrary position when you start everything, it will send you a number. And that kind of, let's say, mechanical arrangement of the magnet and the sensor will result in some kind of like pre-made number. So whenever you start the encoder, you will get a certain number based on the position of the magnet, and you will not get 0 in that position where you started the encoder. Therefore, you have to do this manually. So that's what happens here. So we read the angle recently, and we just subtract the very first read number from that. And then here we have to do some kind of trick. So we have to sort of normalize it. So if the calculated angle is negative, we have to add 360 to it, so we don't get funny numbers. And this is also explained with some drawings in my previous video, so once again, check it. And now we have to check the direction and have to check some other details in order to get the final number of the displacement in degrees. So that's what we do here. So we check if the corrected angle, which we just recently calculated here, is inside one of these sectors. And if it is in one of those sectors, then we update the value of the quadrant number. So that happens here, as you can see. And we can print this position if we want, again, on the serial port. And here what we do is that we see how the quadrants were changed. And if they were changed in a certain transition, you can see it here, for example, then we know that we were in the clockwise rotation. And then here, if it went in the other direction, that was the counterclockwise rotation. And then, based on this, we can express the number of turns that we have done. And why is that important? Because we can have the total angle, so the total accumulated motion of the shaft, and that is the number of turns times 360, so that's like how much turns we did, plus the current position within the 360 range, so 0 to 360. So that is our absolute position on the shaft. And then here we can print it, but actually I do not need this. So then we have the total angle 1, and then we have everything. So then this same thing happens with the other encoder here, as you can see. And one more thing is that this function, it is running in the setup. So this is the check magnet presence. So this just checks if the magnet is close and if it's close enough, and so on and so on. So what we do here is that if the magnet is not properly adjusted, we get stuck in this part. So then we reach the encoder, and then we read the status of the magnet, and then we just see what happens. And while the magnet status, certain numbers inside the whole number that we get from the register does not fulfill this kind of condition, then we just keep iterating inside this part of the code. So then once this is fine, then we escape from this part, and then the code can run. And then technically this was all. So as you can see, once more, we check if we press the button, so we know that we have to move in the menu. And then we read the joystick's value. And then if we have to run the motor, because for example we move the joystick to a certain direction, then we do one step, so every iteration in the loop will result in one step. So you should not use any delays. That's why I use these kind of timers, let's say, because if you have delay in the run speed or any kind of stepper motor motion, then the steps will be not performed properly. So no delays, please. And then once we stepped, we have of course new positions if we move the motor, so we have to update the LCD. And then of course we also have to read the numbers. So we have to read the position of the two encoders. So maybe this makes more sense if I put it here, because then we read really the most recent information. So we ran the motor, we check the encoders, and then we print the values of those encoders on our display. And then this goes over and over. So this was all. And as I said during my demonstration, probably this was this last video in this MINIQ table project, because now I'm more or less fully satisfied with this. I think the only improvement that I can do is the mechanical improvement of the MINIQ table, but that will be a new MINIQ table, so that won't happen in the near future, because I want to put my resources in other projects. So this was all. But now you can see that this kind of MINIQ table or any kind of configuration based on two stepper motors, so your own for example XY table or some kind of stage or anything, can be moved in this way, can be read with this kind of precision, and so on and so on. So you can basically fit this project on any kind of two stepper motor configuration things. So I can finish this video here. Please don't forget to visit my website, because all the resources are uploaded there. This source code, the wiring, and some other information will be there. So don't forget to visit my website. I hope this video was useful. I hope you can use this kind of knowledge and this kind of code for your own applications. I hope you learned something, and see you in the next video.